Okay, it's Friday the 13th. Happy Friday the 13th. There is a new cap up. There will be posted, I'm going to try to get to this afternoon, equation sheets for exam 3 next Friday in class. I have only heard one person so far who is interested in taking that one remotely. You are at that camp. Right. So I don't think I'll be finishing completely the exam 3 stuff today. I think it'll spill over a little bit on Monday. But then we'll be starting on Monday, Wednesday, the next homework set, which will not be due during Thanksgiving week. You'll have that week off from Kappas, but it will be due the following Thursday. And there will be a Kappa due each of the next 3 Thursdays after Thanksgiving. So that last Thursday is the last Thursday of classes. Normally that would be exam week, but there is no exam week this semester because they just decided to have regular classes up to the end of the semester. So we'll have some sort of final assessment to determine how they work. But it will be either happening that Friday or the next Monday, which would be our last class, which is the last day of class, which is the 20th. I can't remember. It's something like that. I think that's right. The 17th is the Thursday before, and the 18th would be Friday, 19, 20, I think 21 is the anyway, that's as far as just giving you a preview about what's coming up. And where. But today's an exciting day. Because we get to talk about one of the most important laws of all of physics. I know, I hate to build you up like this, but it happens to be a really important monumental day. And it's only taken us 2/3 of the semester to get here. So, all right, you can go away if you haven't, do the top hat thing if you haven't already. We're going to take a brief hop now to chapter 20. So far we've been talking about, I haven't explicitly said this, but we've been talking about thermodynamic processes that are reversible. In other words, I have a piston, I have a gas containing a cylinder with a piston on top, and I can add some pellets, some weights to that piston to make it slowly move down. I can remove those weights and have it slowly move back up. These are all reversible processes, right? Anything that we are thinking, and they're all happening slowly. I haven't really said this, but it's true. We're allowing all of these things to happen by themselves. We're not increasing volumes by ripping things apart. We're not decreasing volumes by smashing them together. We are letting things happen in a slow, thermodynamically equilibrium kind of way. That's sort of the definition of or how you make a process reversible. You do it slowly. If you let it happen slowly on its own, then you can usually reverse that process and have it go back in the other direction. Now, not all processes are reversible. You can probably think of lots of processes that are non-reversible. Baking a pie. You throw that pie in the oven, and it comes out a baked pie. There's no way to unbake that pie. Cracking an egg, popping a balloon. These are processes which are not reversible. You can't just do the opposite of what you did to make it that way and have it go back to the way you found it. So we're going to be thinking about irreversible processes now, and what makes a process irreversible as opposed to reversible. What is different between those two things? So here's a simple example. So irreversible processes. Irreversible processes. So far we've been talking about reversible processes. What about irreversible processes? So for example, here is a hot object. Here's a cold object. and I put them in thermal contact with one another. What's going to happen? If you wait long enough, they'll reach some equilibrium temperature, right? Energy will flow from the hot object to the cold. That's what we know will happen. That is an example of an irreversible process. Once you have done that, you cannot undo that without introducing some other energy or doing some other thing to make that happen. It will not ever go back to the way it was on its own. Why? It doesn't violate any laws of physics that we've thought about so far. Energetically, there's no reason why more energy shouldn't be contained in the hot object and the low object even in the cold. There's something else at play here in irreversible processes that we need to think about. So, heat, so I'm just going to write this down so that you have it in your notes. You know, I've said this, but heat flows from hot to cold. It never happens in reverse. Why? Energetically, that's fine. Physics hasn't yet told us where the energy should be located. It only tells us that it has to be conserved. But it would be perfectly, from conservation of energy, fine if it flowed back from the cold object back to the hot object, or separated itself again in some other way. But that never happens. And the reason why that never happens is the second law of thermodynamics. We're going to write down 3 different formulations for this law, because it's not just because it's so important, but because you can think about it in so many different, unique ways. So I'm going to write down the first one right now. This is take 1. And this is Clausius's formulation of the second law of thermodynamics. Okay, I'm closing the attendance now. 2, 4, 6, 8, 10, 12, 14, 16. That's everybody. Okay, because that's less than half the class is actually physically here right now. Okay, so basically it's what we just said. Heat never flows spontaneously. Never flows spontaneously by itself without any action. Spontaneously from a colder object to a hotter object. This is more important and subtle than you might think. And it has wider ranging implications than you might think. For instance, this is, so says people who are smarter than me and have thought about this way way longer than I have, really the only law of physics that you will ever encounter that is not time reversible, that has a preferred direction for time. Almost every law of physics that you could think of, if you play the movie forward or backwards, it works just fine. But for irreversible processes, except for irreversible processes, where you have some weird second law of thermodynamics thing going on, that makes it weird to think about these things happening backwards. Some physicists have conjectured that the only reason why there is a preferred direction of time, and really only a time flow at all, is because of the second law. Without something like this in place, it might be that time would have some non-seemingly uniform moving in one direction and follow. I can't imagine what such a universe would look like, so I can't really describe it to you, but that's what people who think about these things say. So this is a very important law of physics, and it can be stated as simply as that. Here's another way to say it. Here's take two. Another way to say it is impossible to convert the heat from a single source into work. Convert the heat from a single source into work without any other effect. In other words, this is the Kelvin formulation of the second law of thermodynamics. In other words, there is no perfect engine. There is no perpetual motion machine. More on what we mean by engines and how that all works and heat sources in a moment. But now let's think about irreversible processes. Back to irreversible processes, and we'll think more deeply about these formulations as we go. So back to irreversible processes. So here's a thought experiment. Actually, you don't even need to make it a thought experiment. We could physically do this experiment in this department if we wanted to. Let us imagine this irreversible process. We have two containers. We take one of those containers and pump it out, evacuate all the atoms, nothing in there. And the other container, which may be exactly the same size, we have not evacuated, and it contains maybe gas, room pressure, and whatever, right? And there's a little valve that connects the two. The irreversible process that I'm thinking about doing is opening that valve, right? What happens? As you know, there's a vacuum one, half of the gas will immediately get sucked or move into the other half, and then you'll have some equilibrium situation where the pressure gets equalized very quickly. Right? This is an irreversible process. Why? Because there is no situation where it will ever happen where all of that gas ends up back on one side. Unless there's only a single atom or something. If there is a macroscopic number of atoms, it will never happen that all of the atoms end up back on one side of the thing. Which is good. It means that, there isn't in this room going to ever be a time when all of the atoms are on this half and that half of the room can't breathe and this half of the room is breathing just fine. That never happens, and it will never happen. But why? Again, energetically, there's nothing stopping that situation from happening. But the second law of thermodynamics tells us that it can't. So there's something else besides energy, though, that's keeping these atoms distributed through both sides of this container. Okay, so, right. I'm not going to draw that. You can draw that in your notes if you want to. I'm just going to write gas and vacuum connected by a valve. Open valve. Gas spreads through both sides. Will it be exactly even? Will there be, if these two volumes are exactly the same volume, will there be exactly the same number of atoms on one side than the other? Maybe, maybe not, but it'll be close. And there will never be a time when the vast majority of them will be on one side or the other. And if you wait long enough, there will be times when side A has a little bit more and side B has a little bit more, maybe, but that's should average out over time. This cannot be done. This cannot be undone without help, without another seal off, vacuum, a lot of energy, it takes a lot of work and energy and effort to get to reverse this particular process. This cannot be undone without help. Why? There isn't anything energetically that's keeping those particles on different sides of it. There is something else that is keeping those particles on opposite sides of the tank. It is not energy keeping them there. It is something else we call that something else. We call that something else? Do it. Entropy. And we, of course, call it capital S. Because why not? What is it? What is this thing called energy? Well, we'll be discussing that over the next couple classes. For now, know that it is like total energy, like temperature, like pressure, like volume. It is a state variable of our gas, of our fluid, of our system. Which is going to be really useful. If you go from point A to point B on a PV diagram, no matter what path you take, the change in entropy in going from one point to the next has to be the same. And that's going to be useful for us later on. Unlike Q or W, which will depend on the path, entropy is a state variable that depends only on the specific state of the fluid you're talking about, not on how you happen to get there. And here's how you define it. Delta S, well, one way to define it. There are other ways to define it too. But this is an interesting way to think about it. Delta S, so the change in entropy as you go through some thermodynamic process, obviously is the entropy of the final state minus the entropy of the initial state. And that's going to be defined to be the integral, or is equal to the integral from initial to final state of dq over t. With the caveat that this is for reversible cyclic processes. So, for instance, that example that we we're just talking about where you release the valve and let all the molecules through is not a reversible process, and you cannot therefore calculate the change in entropy by this particular thing. In fact, it doesn't make any sense. There's no Q at all in that particular system, right? You have a totally insulated system, you just open the valve, gas expands. So, if a process is reversible, then delta S equals 0. And if a process is irreversible, then delta S is greater than 0. With some caveats that we'll get to in a minute. Okay, what are the units on this thing called entropy? You should be able to tell just by looking at the definition that we just made. Anytime you write down something new, it's useful to know what units it has. What are the units on Q? Yep, and T? So it is joules per Kelvin. Okay. Let's go back to this example that we're just talking about. We're interested in knowing how the entropy has changed in going through this process. Opening the valve and letting it expand. So see if we can calculate it. Well, let's just think about this. So we want to know how the entropy has changed in opening that valve, right? Let's say this is going to be a half example. We're not going to finish it. I think we'll finish it later on. 1 mole of gas is contained on the left side of a container. What is delta S when we open the gate? Now, this is a free expansion of the gas, right? How much heat have we added? Nothing. How much has delta E changed of the gas? What's the work of the gas? Now, you might think it's expanding, but it's not actually doing work on anything since there was a vacuum there. So work is also 0. The volume has expanded technically, but you're not pushing on anything, so you're not doing any work. Work is also 0, right? So you might think that delta S therefore is 0 because of all this stuff happening. It is not. Because this is an irreversible process. That's what we created. So how can we calculate it? Well, we can only use that formula if you have some sort of cyclic reversible process. So how are we going to go about how would we go about calculating delta S? We have the benefit of knowing, though, that S is a state variable. So any way that we can get from our initial point to our final point will give us the delta S, even if it isn't the path that was actually taken by that gas. But if it's one that makes it easier to calculate, we can use it, and we know this is just a state variable, delta S must be the same no matter what path we took together. So the trick to doing these problems is don't look at the process that was actually done, try to find a reversible process that would take you from the same initial state to the same final state by some process that is reversible and is slow and is thermodynamic. Can you think of a set of steps that you could go through to enact the same thing and have the same end state that would be reversible and cyclic? What's true of the temperature before and after you open the valve? It has to be the same. Why? Be careful. You can't just use Q equals C and delta T, because remember that isn't really what temperature is. And you have to be careful because this is a way non-thermal. What is, though, a measure of temperature? Yes, but one of those 3 variables that I wrote down below is really related to delta T. If you don't change this one of these 3 variables, the temperature actually hasn't changed. Which of them is it? It's delta E. Delta E tells you whether or not you've changed temperatures, really. If delta E is 0, then delta T is also 0, which is not true of Q or W. That's important. Even though we've defined delta T with this Q thing, It's messed up because of, this is why you need CPs and CP, it's all messed up. Anyway, so we know that this is you can get to that same state by doing an isothermal expansion to double the volume, right? If you do the same expansion, but isothermally, and again, you're letting this is going to be a thermodynamic process. It's going to be completely different than the one we just did, but you can imagine doing it isothermally, adding some heat energy, letting the gas expand, doing work such that delta E is 0 to get to the same change in volume that you got just by releasing the valve. That you do have some Q involved, and you do have a thermodynamic process, and it is cyclic and reversible, and you could actually calculate the delta S of that particular transition, and because S is a state variable, it must be the same delta S as if you do any other step, including just opening the valve and letting it expand freely. So that's going to be some trick to solving next week's homework problems is, even if you can't solve delta S for the process that you're looking at, if you can find another process that takes you to the same state that is easy to calculate, do that, and it should be the same delta S.
Dr. Steinhauer, I have a question.
Yeah.
So if that formula up top is only applicable for reversible and cyclic processes, but if a process is reversible, then the integral always equals 0. So why is it helpful?
Yeah, so when I wrote this down, I realized it was probably a bad thing to write down. So the question was, if delta S is always 0 for cyclic processes, why is that useful? It's not really 0 for reversible processes. It's 0 for cyclic cycles. So I should really say, if the cyclic process is reversible, delta S equals 0. If the cyclic process is irreversible, then delta S is greater than 0. So you can certainly have reversible processes where delta S is greater than or less than 0. That is I probably shouldn't have written down what I just wrote down. In fact, what do I mean by cyclic? A place where you get back to the place you started from. Question.
Well, how can we have a cyclic process if it's irreversible, if it goes back to the way it was? Like the situation that we have now, where if we add energy, we would be able to get back to where we were, but it's unlike baking a pie, where
right.
It's not cyclic or
right.
reversible.
Right. Right. So yeah, there's probably even more. And as I was writing this down, I thought, man, this really isn't right. So maybe there is going to be this is going to be an important thing. Delta S equals 0 and delta S not equals 0. Let's take a step back from that though. It is certainly possible to have negative entropy in a process. It is possible to have positive entropy in a process that is reversible. But you can't go through an entire cycle and get back to where you started from and have it be delta S equals 0 unless you have a perfectly reversible process. You couldn't, in other words, unless delta S is 0, you can't do the opposite and get back to where you started from without a lot of extra energy coming in from elsewhere. Does that make sense? Okay. Okay, so let's think about engines. And I will make a note that this is probably not a good thing to write down at this point in the lecture. Okay, so when I say engine, you probably are going to immediately think of, and I apologize because I thought my iPods were working this time. I don't think they are. And now that I see, I don't even see them here, which is sad. I have to investigate this later on. Anyway, I'll try to stay close to the point. When I say engine, you're probably thinking of you see an engine. That's really not what I'm talking about when I say engine. Right? Those are all internal combustion engine. You're generating energy by burning fuel fossil fuels. You're generating energy by breaking molecular bonds of molecules. I'm talking about an engine that has as its fuel source nothing more than a hot reservoir and a cold reservoir. It turns out that you can do work and turn that temperature difference into work with some thermodynamic process. And that's what we're talking about. We're talking about a thermodynamic engine, where all you have as a fuel source is a hot object and a cold object. How are you going to make that do work? Okay. We're talking about thermodynamic cycles with hot and cold reservoirs, not internal combustion engines. Not internal combustion engines. Now, internal combustion engines are interesting and fascinating, and there are a lot of thermodynamic principles in play in thermodynamic engines, including cyclic processes, but the energy input is not from some heat reservoir, it's from the burning of these fossil fuels. So it's a rather different thing. Okay, so our goal is to convert heat energy, Q, into mechanical energy, W. Can we use our two different objects at different temperatures to do work? Our goal, convert heat energy into mechanical energy. Thanks, that was terrible. I apologize for that indecipherable scroll. But all it says is convert heat energy Q into mechanical energy W. The second law we've already seen of thermodynamics says that you can't do it perfectly. But how good can you do it? It turns out that the most efficient engine to do this was postulated by a guy named Sadi Carnot in 1824, and we call it the Carnot cycle. I think he was a French physicist. So this is the ideal engine. This is the most efficient way you can do it. Carnot engine, or the Carnot cycle. So here it is. I'm going to, well, this picture is important, but let's write down the steps, and then we'll think about how it looks on the PV diagram. So, stages. So, let's actually draw our PV diagram here. We need the system plus, so our system is going to be some gas system with some piston where we can move things up and down, and two reservoirs, a hot reservoir and a cold reservoir. That's what we need for the system. So the system, which is whatever gas and piston system you're working with, plus two reservoirs. One at T hot and one at T cold. Okay, so let's say we start off, so this is, let's say, some isotherm for T hot or T cold, and this is the same isotherm for T hot, not the same isotherm for T hot. Okay, we're going to start somewhere down here. Let's call that our initial position. We've got some pressure and some volume for our gas. And our first step is to oh, I lied. We're going to start down here somewhere. Our first step, although I think this is step, it doesn't really matter. It doesn't matter where you start. We're going in a loop. We're going to get to all four of them eventually. So but though I have it written in my notes right now, you start with isothermal expansion. And I haven't yet gotten it right, because isothermal expansion has to start way up here, at the hot reservoir. We'll get to all those other points eventually, don't worry. But isothermal expansion means we're moving down along that isotherm, right? That's step one. We know that for isothermal expansion, delta E is 0. We know that heat is added and work is done. We know that Q equals W, in fact, for an isothermal expansion, and both of those will be positive if we're getting bigger. So our volume is expanding, and we're adding heat energy from our hot reservoir. Okay, there comes a point where we're going to stop adding thermally expansion. And then step 2 is going to be adiabatic expansion. We're going to remove it from our heat reservoir, where it's no longer going to be in contact with the heat reservoir, but we're going to continue to let it expand. This is going to be adiabatic expansion. As you know, Q equals 0 in this case. Work is done, so the temperature goes down. So that's going to look something like this. Remember, our adiabatic curves are steeper than our isotherm curves. And so you can get back to T cold. This is TH. This is T cold. And we do that until the gas cools down to the temperature of our cold reservoir. We then undergo isothermal contraction. Heat is removed. Delta E is still 0, but W is negative, and Q is, and energy is being, thermal energy is being removed from the system. And that will look like this. Isothermal contraction, getting smaller along the TC isotherm. And again, the TC is important because you're dumping the thermal energy, you're adding negative heat energy. In other words, you're dumping thermal energy from your system into the cold reservoir. And finally, adiabatic contraction. Again, Q equals 0. Work is now negative, and temperature goes up. And we get back, we've done this right, to where we started from. So here is the, I guess that is exactly how they did it here. A, B, C, and D. This is the picture from the book talking about the Carnot cycle and the Carnot engine, starting at this point on the pressure volume chart, expanding isothermally. And this arrow is important because heat is being added from the hot reservoir at this point. To keep it the same temperature, even though work is being done and the thing is expanding, you then remove it from that thermal reservoir, and then it expands adiabatically to this point at the lower temperature, and then you turn it around and go in the other direction. You start compressing the thing isothermally, again, now in contact with the cold reservoir, so energy is flowing from the system into the reservoir until you get to this point. Remove it from the reservoir again, continue compressing it until you get to A. How does this do work? Again, you can sort of imagine how this is going to work, right? What is the work you're going to do? Maybe it is, how is this going to work? So you've got a very small volume at A, right? How are you going to let it expand? Well, you're going to let it expand as heat is being absorbed by, well, I'm going to stop talking about this. In my head, it's now going down to what I thought it was. Anyway, the bottom line will be, you'll be taking pebbles and stones and masses off when it's at its height, and you'll be adding stones when it's at its lowest point. And so you'll be moving these stones maybe from a low position to a high position as this thing expands and contracts. So that's how you're going to be converting the thermal energy of the hot reservoir into work. The network will not be zero. The net energy will be zero, but why will the network not be zero? In fact, what is the network done over the cycle? Graph it. It's the area of that banana. The area under the curve. As you move to the right, the work is positive. As you move to the left, the work is negative. But since the pressure is higher as we're going to the right, the network is positive because it's going to be more work being done on the top than is being undone on the bottom. So this will be a network machine. And the net Q will also be positive. You're also dumping energy into this system as you go around the cycle, from the hot reservoir to the cold, to the system. How much work is done? How much have we actually done? We can calculate it. In the full cycle, we know that delta E has to be zero because delta E is a state variable, but Q and W will not be zero because they're not state variables. So we know that delta E equals Q minus W. Over the whole cycle, that's got to be true, so that we know that Q equals W over the whole cycle. This will not be true for individual steps, at least the adiabatic steps, right? Q will be zero for those, and W will not be zero. Q is only added in steps 1 and 3, right? This is adiabatic. Step 2 is adiabatic, so Q is 0. Step 4 is adiabatic, so Q is 0. So the only Q's we have to worry about are from steps 1 and 2, 1 and 3. So we know that W, the total work done, is the Q tote, which is, I'm going to write this way, however much energy you added from the hot reservoir when you were doing the isothermal expansion, minus however much energy you took away when you were doing the cold. And this is going to, of course, depend on the details of what temperatures and volumes you're actually on. I have put absolute value signs and put a negative sign there explicitly because it's easy to get confused about the signs of these things, right? I want you to understand that Q is being removed here. This Q will be negative, and this should really be a positive, a plus sign, but I want you to know this will always be negative, and this will always be positive. So if you're thinking about energy in and energy out as being absolute value things, you're taking how much energy you added and subtracting how much energy you took away. Okay, how is the entropy of this cycle changed? Again, for the adiabatic stages, Q equals 0. And so, remember, we define delta S to be the integral of dQ over T, also is 0 for the adiabatic stages. The entropy is not changing as we move down those adiabatic curves. But it does change along the isotherms. How much? Delta S is total is delta S H plus delta S on the cold. So these are the two, I'm talking delta SH and delta S cold. Delta SH is how much the entropy changes here, and delta S cold is how much the entropy changes on stage, talking about stages 1 and 3. We're moving along the hot isotherm and moving along the cold isotherm. Well, okay, this is going to be the integral of dq over th plus the integral of dq over tc. Fortunately, those temperatures are constant, right? Though we can pull those out of the integral over these processes because the temperature isn't changing. And so this just becomes 1 over t times the integral of dq, and the integral of dq is just q over that process. So this is simply qh over th minus, because this q is negative, qc over tc. Absolute values. You could move the absolute values and change that negative sign to plus sign, but again, I think it's easier to think about this in terms of positive energies being removed and added, and if that's the case, you need to think about these, that negative sign goes on there. Great. What is delta S for the whole process? The entire cycle. Would it be 0? Would it be 0? It would. S is a state variable. If you begin and end in the same point and you've done thermodynamic reversal processing, which we have, our S has not changed. The S that you gain in one has to be lost in the other. You have to get back to where you started from. So we know that delta S equals 0 equals QH, absolute value of QH over TH minus absolute value of QC over TC. And that gives us this interesting result. The fact that entropy is a physical thing that we can calculate allows us to gain physical insight into some of the quantities that are of interest in these cyclic processes. It is. You can do the Carnot cycle backwards. What would that look like? Well, now you are turning work into heat, right? You're dumping. You're doing work to dump energy from the cold reservoir into the hot reservoir, as opposed to using the energy from the hot reservoir, dumping it in the cold reservoir to do work. You could imagine doing this backwards. One is a refrigerator if you run it in one direction, and it's an engine if you run it in the other direction. But both are equally valid, and you can do it both ways. One of them works positive, and one of them works negative. And one of them, you're moving energy from the hot reservoir to the cold reservoir, and one of the other one, you're moving energy from the cold reservoir to the hot reservoir by doing work. Yep, kind of cool. So which is bigger? QH or Q or QC? They're not the same size. Because TH is bigger than TC. If those things are going to be equal to each other, then QH has to be bigger than QC. Which makes sense. The total work amount, the total Q has to be positive because we're doing net work. More heat into system, so Q is positive and W is positive, and that's what engines do. They turn, these thermodynamic engines turn heat energy into work. Okay, I'm out of time now, but our next step is to calculate the efficiency of this engine. And you'll need that efficiency for some of the problems on next week's homework, but you still do have enough to do most of the problems already on next week's homework. So stay tuned. We will recast the second law of thermodynamics in at least one more way and think about efficiencies of engines and wrap up our entire thermodynamics. Have a good weekend.